Hi students, very good morning. In this lecture, we are going to deal with respect to the vapor pressure. Okay. See, when the vapor comes into the existence, whenever any substance gets evaporated, then it gets converted into the vapor. And whatever the pressure exerted by that particular vapor, that is called as vapor pressure. See, again I am repeating. Any substance to get into vapor means first it should get evaporated. Don't go for the sublimation. We are talking with respect to solutions, right? Solutions means it will be in the liquid state. For any liquid solution, to get into a vapor means it should get evaporated. So after getting evaporated a liquid solution, it exerts some sort of pressure on the container of the wall. Okay, that pressure it is called as vapor pressure, and that comes due to the evaporation. Let me take a container. It is consisting of the entire liquid particles of only one type of component. Either it may be complete alcohol, complete water, or complete benzene, anything. So the molecules present on the surface, those are called as the surface molecule. Apart from the surface, the remaining molecules are called as bulk molecules. Okay. See, always remember, evaporation starts from the top layer, not from the below layer or bottom layer or from the bulk molecules. So always the surface molecules gets evaporated. Why the surface molecules gets evaporated? This is the question that arises. Okay. Then the reason for that is, if any molecule is present in the bulk, see, let me take this is the bulk molecule, means it is present in the middle or somewhere here. Okay. Any molecule whichever it is present in the bulk, it is equally attracted by all the molecules surrounding it. So surrounding there will be on all directions, front, back, as well as up, down, in all corners. See, if you talk in terms of direction, north, east, west, south, northeast, northwest, southeast, southwest, as well as front and back. All the directions, okay, all the directions of this A, whatever that are surrounded by the molecules, that molecules will attract with equal force of attraction this one, this central molecule, so that this molecule will not get evaporated. Okay, so if you see the surface molecule here, see at the bottom as well as the sides, beside as well as the bottom, you are having molecules, it will attract that one. But the top surface, you are not getting attractions. So what happens? It is experiencing less force of attraction from these beside molecules. Here, in all directions it is experiencing the force, so that it can't get evaporated. For this molecule, it is getting attractions only from this side. Okay, what happens? It is experiencing less force of attraction from the surrounding molecule, so that this molecule will be having some more amount of energy. So more amount of, simply we can say, kinetic energy, so that this molecule tries to move in the vapor state, so that it gets evaporated. So whenever the first layer has gone, the second layer will become again the top layer. Again that layer will be less experiencing the force from the surrounding molecule, so that it also gets evaporated. In the same way, if you take a glass of water and keep in your room and you don't disturb it for 3 or 4 days, the entire glass will become empty. Why? Means the surface layer gets evaporated into the atmosphere. Suppose if this is happening in the open vessel, right? If it is happening in the open vessel, this condition will be happening both in closed as well as the open vessel. If it is happening in the open vessel, weight of the liquid, what happens? The weight of the substance, whatever that you have taken initially, it gets decreased. So vapor pressure is not talked in the open vessel. So vapor pressure is always with respect to closed vessels, not with the open vessels. This is what you are seeing. I have taken here open vessel, right? It gets evaporated into the atmosphere. Okay. And if you talk the evaporation with respect to the closed vessel, means evaporation that is occurring in a closed vessel, what happens? Evaporation occurs in a closed vessel. If you take a closed vessel, means you are taking glass of water and you are closing it on the top. There is no contact of the water molecules with the atmosphere, right? So what happens now? Evaporation occurs. So if you take any liquid in a closed vessel, what happens? Evaporation occurs and vapors cannot escape from that particular vessel. So as it is a closed container, so what happens? Sometimes up to certain extent, the number of vapors goes on increasing, and they will hit the top wall of the container or side walls of the container. What happens at one particular stage? If they are going on hitting, what happens? The vapor also gets deposited at the liquid particles on the wall of the container. At one particular point, number of vapor pressure or number of vapors getting converted into liquid and liquid getting converted into vapor will be equal. See, already you have learnt in your first year, equilibrium chapter. There will be equilibrium in a closed vessel. So what happens if you are keeping a liquid in a closed vessel, the number of particles getting evaporated and the number of particles getting condensed into the liquid state will be equal at one particular point. Okay, in first at the starting point, number of vapors will be more. Okay, what happens if vapors are going on increasing? The molecules will be getting settled at the top, and one molecule will be settled on that only. One more molecule will go on settle on that only. Still many more molecules will settle on that, so that it will form again liquid substance. Okay, the number of vapors will be getting above and the number of liquid particles will be getting down, whatever that have been deposited at the top. What happens? So that there will be an equilibrium at one particular point of time. The number of particles getting evaporated and the number of particles getting condensed into the liquid state will be equal. Okay, so then the pressure of the vapors above the liquid surface. So number of particles is getting evaporated. See what I have said is number of particles getting evaporated. They get settled on the top of this one. Number of particles still are going in. They will get more deposited. So that what happens? This entire vapor, whatever that at the top is present, that will be getting converted into again liquid. It gets dropped into the liquid again. And the number of vapors are getting, the surface one produces vapor and the number of particles are getting down from the top of the container. Why? Due to deposition of more number of vapor particles. Again it gets converted into liquid. So whenever this vapors are getting, the pressure exerted by vapors, these are the vapors, it is getting back, and these vapors exerting pressure on the liquid surface, that is called as vapor pressure. The pressure of vapors above the liquid surface, the pressure exerted by the vapor, it is called as vapor pressure. So the pressure in this, as this is the pure solvent, for pure substances, whatever the pressure exerted, it is taken as P naught A, as it is A type of solute or solvent, anything, A type of solution, we can't talk solution, A type of substance, component, you can say, because solution is again solute plus solvent, right? So my intention is, whatever the vapor pressure that is exerted, the pressure exerted on the surface of the liquid, okay, that is called as vapor pressure. As it is a pure component, it is P naught A, vapor pressure of pure liquid. So now let us discuss the factors which affect the vapor pressure. What happens? It doesn't depend upon the shape or size of the container. So even though the container may be very large, it doesn't depend, because you know that pressure is a pressure is intensive property. It doesn't depend upon the amount of the substance. In thermodynamics we have learnt. So pressure is nothing but force acting on unit area. So even though if you increase the container, force acting on unit area will be the same. Even though the number of particles getting evaporated may be changed, but the pressure, force acting on the unit area will be again the same. Okay, so vapor pressure does not depend upon the shape as well as the size of the container. It depends upon the nature of the substance. How it depends? Suppose if I take a water molecule as well as ethyl alcohol. See, in ethyl alcohol you will be having hydrogen bond, in water also you will be having hydrogen bond. One water molecule will form 4 hydrogen bonds, whereas ethyl alcohol will form only 1 or 2 hydrogen bonds. Okay. See, where there are more attractions, here there is more force of attraction, so that it gets less evaporated. Here, less force of attraction, it gets more evaporated. So vapor pressure of which one will be very high? Vapor pressure means it should get converted into vapor. Among these two, which easily gets converted into vapor, this one will get easily converted into vapor, because we are having only less number of hydrogen bonds, here more number. So vapor pressure of ethyl alcohol will be greater compared to the vapor pressure of the water. So indirectly you can say that vapor pressure is inversely proportional to the force of attractions. If there are more force of attractions, the vapor pressure will be very less. So P naught means pure vapor pressure of ethyl alcohol is greater than pure vapor pressure of water. Okay, pure substance of H2O. Suppose if there is an example like C2H5OH, this is glycerol, CH2OH, CHOH, CH2OH, and CH2OH, CH2OH. This is called as glycol. You are having the 3 components, ethanol, glycerol, glycol, which will be having more hydrogen bonding. See, here to here, hydrogen bond formation, here also formation of hydrogen bond, this one with another one. Okay, this one will form with side also, with another glycol. It forms intramolecular as well as intramolecular hydrogen bonding. This one also forms intermolecular as well as intramolecular. This one forms only intermolecular. So in which interactions are very less? So in this interactions are very less, in this very more, in this somewhat better, intermediate between these two. Okay, so here more interaction, so vapor pressure will be very less. So P naught of glycerol is very less compared to P naught of glycol, compared to P naught of ethanol. So now for a solvent you will be adding a substance, right? Solution is nothing but what? Solute plus solvent. The solute may be of two types. One is volatile and the other is non-volatile. So non-volatile we will be learning regarding colligative properties. In this lecture we will be learning regarding the volatile substances. The solute is also volatile. The solvent is also volatile. Volatile means what? Which gets evaporated. Any substance which gets evaporated, it is called as volatile. Okay. So the substance or the solute, whatever you are adding to the solvent, it may be volatile or non-volatile. If you are non-volatile means you can say that solids. Suppose if you add sugar to water, water will be getting evaporated, solvent. Sugar is a solid, it will not get evaporated. Okay, for P naught of solids it is equal to 0. So the pressure exerted by the pure solid is 0. So what does this indicate? It has no tendency to get evaporate. Example, if you take urea, glucose, sucrose. These are the generally taken terms. Urea, what is the formula of urea? NH2CO, NH2. Glucose is C6H12O6 and sucrose is C12H22O11. If you go for the molecular weights of urea, it is 60, glucose is 180 and sucrose is 342. Simple. Non-volatile solute means it doesn't exert any vapor pressure. Only the vapor pressure exerted here, it is only by the solvent, not by the solute. Here if you take volatile substance, suppose if you are adding alcohol to water, water also gets evaporated, alcohol also gets evaporated. So both gets evaporated. The pressure will be different, the pressure of the solution. Here only due to the solvent, not due to the solute. If you take both are non-volatile, solvent is non-volatile, solute is non-volatile, then no need to talk vapor pressure. If solute is not getting evaporated and solvent is also not getting evaporated, what is the use to talk with respect to pressure? Okay, so one is volatile and the other one is non-volatile. This is condition. If both are volatile, this is the condition. Means what does that indicate? P naught of that substance, whatever you are adding, it is not equal to 0 because it has some vapor pressure. Example, what happens? Example, those are taken as water, methyl alcohol, ethyl alcohol, benzene as well as toluene. So many they are there. This is the condition. And vapor pressure. See, vapor pressure depends upon what? On temperature. Now we have talked three things. It doesn't depend upon the size or shape of the container. It depends upon the nature of the substance. And vapor pressure, it also depends upon the temperature. If you increase the temperature, what happens? Evaporation increases. If evaporation is increased, what happens? Vapor pressure increases. This is the graph vapor pressure with respect to temperature. Okay, students. Now you are making a solution. See, vapor pressure of the solution containing two volatile liquids. You are going to calculate this one or you are going to learn this one. Right, solution. The solution is made up of solute plus solvent. Solute is volatile liquid and solvent is volatile liquid. Both are you are taking. And always I have said take solute as B, solvent with A. So if it is in pure condition, solute is in pure condition, means before mixing with the solvent, the pressure exerted is P naught B. And pressure exerted by the solvent before adding solute, it is P naught A. So I am taking this one. Here this is pure content of A, this is pure content of B. So whatever the pressure exerted here, it is P naught A. It is the vapor pressure exerted by pure A component. And here in this container, it is P naught B, vapor pressure exerted by pure B component. On combining these two, it forms a solution. Okay. Here solution is found, right? After by mixing of A and B. So P total, can I say that P naught A plus P naught B? You should not tell in this way because this is solution. P naught A is for pure one, P naught B is for pure one. Here you are getting solution. This is A plus B. Okay, then you can't write in this pattern. You can write it as P total, total pressure exerted. These two are getting evaporated. B is getting evaporated, A is getting evaporated, right? The pressure exerted here it is PA plus PB. Okay, partial pressure of A plus partial pressure of B. Because you are having two pressures, by combining these two you are getting this one. So it is having in total pressure, it is having some part, it is having some part. So can I call partial of this pressure, partial of this pressure. So P total will be equal to partial pressure of A plus partial pressure of B. Right, students? Because it is a mixture. Right. Partial pressure of A. It depends upon the number of particles of A. So more the number of particles of A, more will be the partial pressure, means more particles will be getting evaporated, more will be exerting pressure. If I go for partial pressure of B, if more the number of particles of B, more will be the partial pressure. Same thing. See, it's very simple. More the number of particles means mole fraction will be more. Okay. This is zeta, right? More the number of particles of A, more is the mole fraction, more will be the partial pressure exerted by that. If more the number of particles of B, so it depends upon the, it exerts more vapor, more pressure, so that this will be equal to PB. So can I write this? And this is what it is called as Rolle's law. What it says is, in a solution, you are taking a solution, the partial pressure of each component, this is the partial pressure of the each component, is directly proportional to the mole fraction of that component. See, partial pressure of the component is directly proportional to the mole fraction of that component, because if the more number of the particles, more will be the partial pressure. That is what it is said by Rolle's law. So again I am repeating, what is Rolle's law? In a solution, the partial pressure of each component is directly proportional. The partial pressure of the each component is directly proportional to the mole fraction of that particular component. So if I take mole fraction of A is nothing but number of moles of A by total number of moles, mole fraction of B, it is nothing but number of moles of B by total number of moles. And we know that all the summation of the mole fractions in a given solution will be equal to unity. Okay. Right. Here what I am doing is, already I know that mole fraction of A is directly proportional to the partial pressure of A. If I remove the proportionality, I will be getting PA is equal to K. I am taking some constant is equal into mole fraction of A. I want the value of K. Okay. So what I am doing, let us consider a pure solution. Pure A is present. Initially I have taken one container, only A is present. Then what happens to the mole fraction of B? There is not at all, there is solvent, or there is no solute at all in that. So that XB will be equal to 0, XA will be equal to 1. Mole fraction, you know that XA plus XB is equal to 1, right? Solute plus solvent, solute mole fraction plus solvent mole fraction will be equal to 1. Okay. Now what I am doing, I want the value of K. I am taking only solvent particle now. I am taking only solvent, means mole fraction of solute will be equal to 0, XA will be equal to 1. So that I know that PA is equal to K into XA, and the XA it has been 1. K is equal to P naught A. So this, you keep this P naught A value here. So PA will be equal to P naught A in place of K. P naught A into mole fraction of A. So partial pressure will be equal to P naught A into mole fraction of A. In the same way you can do for PB. Partial pressure of B is directly proportional to mole fraction of B. It is equal to K into mole fraction of B. I want the value of K. What I am doing, I am taking only the solute particles. If I take the pure solute, what happens to the mole fraction of A? It will be equal to 0. And mole fraction of B, it will be equal to 1. So PB is equal to K into XB. XB is nothing but this is xi B, or zeta B is equal to 1. So K will be equal to P naught B. As it is in pure solution, partial pressure whatever that is exerted will be equal to the pure substance, because you are taking pure substance, right? This is partial pressure. This partial pressure will be equal to P naught B, because this is a pure solution. You doesn't have anything. So K will be equal to P naught B. Now you keep P naught B, this one in this equation. So PB will be equal to P naught B into mole fraction of B. Right? Now what is the total vapor pressure? And total vapor pressure is nothing but PA plus PB. PA you have got this value. P naught A mole fraction of A plus PB is mole fraction of B into P naught B. So this is the content what you are having, and P naught A and P naught B are determined experimentally at a given temperature. If you change the temperature, these values will be changed. So the temperature should be constant. At particular temperature, these are determined. So let us take some examples with respect to this model. This is the entire concept whatever you are having with respect to the volatile liquid as well as the volatile solvent. If 0.78 grams of benzene and 0.92 grams of toluene are mixed. Toluene means benzene ring with CH3. This is only benzene ring. Find the partial pressure of benzene, partial pressure of toluene, and total vapor pressure if pure benzene is exerting 400 mm Hg and pure toluene is exerting, toluene let me represent it with TL, representing TL, it is exerting 200 mm Hg, and he has mentioned in terms of grams. To get the mole fraction, what you should do? This one should be converted into moles. So number of moles of benzene will be equal to weight by molecular weight of benzene. He has mentioned 0.78. Benzene is C6H6. Carbon is 12. 12 into 6 is 72 plus you are having 6 hydrogens. 72 plus 6 it is 78. So number of moles of benzene is equal to 0.01. Number of moles of toluene. Weight he has mentioned 0.92. Go for the toluene structure. Benzene ring on that CH3. The weight will be 92. So that number of moles will be 0.01. Okay. Right. Next, if you go for the mole fraction of benzene, what happens? Number of moles of B by total number of moles. This one. So it will be 1 by 2. Mole fraction of toluene. Number of moles of toluene by total number of moles. Again it is 1 by 2. If you go for the partial pressure of benzene, we know that P naught of B into mole fraction of B. P naught of B, that is benzene, it has mentioned as 400 into mole fraction of B, it is 1 by 2 you have got here. So it will be 200. Then partial pressure of toluene will be equal to P naught of toluene into mole fraction of toluene. So P naught of T is nothing but 200 into half, it is the mole fraction, you will be getting 100. P total will be equal to what? Partial pressure of benzene plus partial pressure of toluene. You have got 200 plus 100, it is 300 mm Hg. That is what you will be getting with respect to that one. Right. Take one more example. Ethanol and methanol are mixed in 3 moles as well as 1 mole. He is asking the total pressure. Pure ethanol pressure is 55, pure methanol pressure is 50 mm. You know that partial total pressure is equal to partial pressure of ethanol plus partial pressure of methanol. Partial pressure can be written as pure pressure of ethanol into mole fraction of ethanol plus pure vapor pressure of methanol into mole fraction. Pure ethanol vapor pressure is nothing but 55, it has been mentioned, into mole fraction of ethanol. How much? Number of moles of this one by total moles. It is 3 by 4 plus 50 into mole fraction of methanol. 1 by total 4. See, 165 by 4 plus 50 by 4, it is equal to 215 by 4, it is equal to 53.75 mm Hg. In the same way, students, this is one more model. You are having two substances, solute as well as the solvent. Both are volatile. If X is taken 2 moles, Y is taken 2 moles, the total pressure exerted is 500 mm Hg. If X is taken 3 moles, Y is taken 2 moles, the total pressure exerted is 400 moles Hg. Find the pure pressure of X, pure pressure of Y. Okay. We know that Pt is equal to P naught X mole fraction of X plus P naught Y mole fraction of Y. If it is 500, it is P naught of X. You should find out number of moles, mole fraction of X. So it is 2 by 5. Next, P naught of Y, 3 by 5. This is first equation. Second equation, it is 400 total pressure. P naught of X, you should find out. Here it is 3 moles. Total moles is 5. 3 by 5 into plus P naught Y, number of moles. This is 2 by 5. So it is 2 by 5. Solve these two equations so that you will be getting P naught X is equal to 200 mm Hg. Py is equal to 700 mm Hg. Right, students? Now one more question. Ethanol and methanol are mixed. Ethanol is taken 0.92 grams, methanol 0.32 grams. Pure ethanol is exerting pressure of 55 mm Hg and pure methanol is exerting pressure of 50 mm Hg. The questions are: find the partial pressure of ethanol and partial pressure of methanol, total vapor pressure, that is Pt, and is asking mole fraction of ethanol and methanol in vapor phase. This is important. See, whatever you are taking till now, mole fraction, those are in the liquid state. Number of moles, whatever you are taking, all the things. Now he is asking in the vapor phase. Okay, and I am representing the mole fraction in vapor phase. It is Ye ethanol and Ym for methanol. These are mole fractions, right? Go for the calculation of number of moles of ethanol. It is 0.02 because weight by molecular weight. Number of moles of methanol, weight by molecular weight, this is 0.01. And mole fraction of ethanol, it will be 0.02 by total number of moles. Combining these two, you will be getting 0.03, that is 2 by 3. If it is 2 by 3, mole fraction of ethanol should be 1 minus 2 by 3, it is 1 by 3. And you know that PE, he is asking PE and PM, right? PE is nothing but P naught of E into XE. You know that 2 by 3 is the mole fraction of this one. P naught E is how much? 55. So 55 already has been mentioned here. 55 into 2 by 3, you will be getting 36.66. And PM, P naught of M into mole fraction of M. P naught of M is 50 into XM is 1 by 3. So you will be getting 50 by 3, it is 16.66. Total pressure, if you sum up these two things, you will be getting 53.33. Now what he is asking? He is asking the mole fraction of ethanol in the vapor phase. The formula is pressure of ethanol by total pressure. This is fraction. Partial pressure to the total pressure. If you do, you will be getting mole fraction. Okay. Mole fraction of ethanol in vapor phase. Remember this. This is in vapor phase, not in the liquid phase. Okay. Why, sir, you are taking this one? In Dalton's law, first year already you know that partial pressure will be equal to mole fraction into total pressure, right? Partial pressure of any substance for the gases will be equal to mole fraction to total pressure. If you send total pressure this side, what happens? Partial pressure of that substance by total pressure will be equal to mole fraction. That is what he is asking. Mole fraction in the gaseous state, because these are gaseous. Dalton laws are gaseous, right? So partial pressure will be equal to mole fraction into total pressure. If you want mole fraction, you send partial pressure, total pressure this side. We will be getting partial pressure by total pressure. That is what here. Partial pressure of that substance by total pressure. Partial pressure of this one is 36.66. Total pressure is 53.33. So for ethanol in the vapor phase, the partial pressure is 0.68. For methanol in the vapor phase, mole fraction. Sorry, this is mole fraction, right? For methanol in the vapor phase, mole fraction is partial pressure of methanol by total pressure. That is 16.66 by 53.33. You will be getting 0.32. Here, what is this? Mole fraction of ethanol. It is equal to partial pressure of ethanol by total pressure. So partial pressure of ethanol is 36.66 by total pressure is 53.33. So we'll be getting the mole fraction of ethanol in the vapor phase will be equal to 0.68. Okay. Right. Let us take the basic content of this one. We are taking two substances A plus B. Both are volatile. For pure substance, this one is P naught A. For pure substance B, it is P naught B. I am representing this one. I am taking, this is X, sorry, this is on the Y axis and this is X axis. And here also Y axis. Okay. What happened? At this point, I am taking pure substance A. At this point, I am taking pure substance B. If I take pure substance A this side, what will be the mole fraction of A? Mole fraction of A is 1 because you doesn't have any mole fraction of B. At this point, it is 0. So if you are having pure substance, it is having mole fraction A means what will be the pressure? The pressure is nothing but pure vapor pressure exerted by A. So I am taking this one, on this axis. On Y axis like this, the pure substance is there, mole fraction is there. Okay, the pressure exerted is this one. If I go on adding B, at this point I am adding B, at this point I am adding B. So what happens to the pressure? It goes on decreasing. See, at this point it is decreased, at this point decreased. So P naught A, whatever that have represented with pink color ink. See, from here it is the original thing, pure substance. By adding B, it is going on decreasing. Because as you are going on adding B, the number of particles of A are getting reduced. Okay, number of particles are not getting reduced basically. As the number of particles of B are increasing, in presence of B comparatively, it is decreasing. Initially, you doesn't have any particle B. After some time, you are adding some particles of B. If you are going on adding on B, at one point, B is more and A are 0. Okay, if you are going on decreasing the particles of A, see here, if you are taking pure B, so mole fraction will be equal to 0 of solute, and this one, mole fraction of B will be equal to 1. So pure B means whatever the pressure exerted will be equal to P naught of B. So P naught of B is highest. So what happens if you add, if you come in this pattern, if A is getting added, A is getting added, so A is getting added, A is getting added, A is getting added, so that here what happens, P naught B is equal to 0. Here P naught A is equal to 0 in this pattern. So this brown color line, it indicates partial pressure. This line entirely indicates partial pressure of B. It is equal to P naught B into mole fraction of B. This indicates PA, mole fraction of A into P naught of A. And this line indicates for solution, PA plus PB. Okay. Take one more question, and this is the last question for this video. Benzene plus toluene. He has mixed these two contents, both are volatile, and total pressure it has been found that PT is equal to 100 plus 60 into mole fraction of benzene. XB is nothing but here mole fraction of benzene. Find the pure vapor pressure of benzene and toluene, P naught B as well as P naught of toluene. He is asking the thing. How you will solve this? Use your analytical skills and solve this. Pause the video. If you are able to solve this, you are good at doing this problem or good at doing this topic. Okay? Right. 1, 2, 3. I am going to explain this question. Right. This is the total pressure. Total pressure will be equal to P naught of benzene into mole fraction of benzene plus P naught of toluene into mole fraction of toluene. We know that mole fraction of benzene plus mole fraction of toluene is equal to 1. Mole fraction of benzene or mole fraction of toluene will be equal to what? If you send this side, it will become 1 minus XB. Why you are taking this one? Because you are having in question 100 plus 60 XB. Right? You are having XB here. Okay, that's why I have converted toluene into XB. 1 minus XB. So I can write P naught of B, mole fraction of B plus P naught of toluene. In place of mole fraction of toluene, I can write it as 1 minus XB. P naught of B, mole fraction of B plus, you multiply this one with 1. So P naught of toluene minus P naught, you are having minus P naught of toluene into mole fraction of toluene. So PT will be equal to P naught of toluene plus, take common here, mole fraction of B, that is benzene, into P naught of benzene minus P naught of toluene. So compare this equation with the original equation, whatever that has been given in the question. So PT is equal to P naught of toluene plus mole fraction of benzene bracket P naught of benzene minus P naught of toluene. This one is equal to same way. P total is equal to 100 plus 60 mole fraction of B. See, mole fraction of B is common. So PB naught minus PT will be equal to 60. And this 100 will be equal to P naught of toluene. So P naught of toluene is equal to 100. P naught of toluene is equal to 100. Now, P naught B minus P naught T is equal to 60. Okay. And you know that P naught of toluene is equal to 100, right? You have got already here. So it is minus 100 is equal to 60. If you send 100 that side, it will be getting plus 100, so that P naught of benzene will be equal to 160. Okay students, I hope that you have followed this video very well. If there are any doubts, you can ask me the questions. Practice your material, whatever that has been sent to you by sir. All the best. Have a nice day. Thank you.